thank you very much for the invitation to this great workshop. And today I'll talk about occupational exoskeletons and human-robot synergy. So this is the title of the talk. I'll talk about design, assessment, and perspectives of this technology. As you said already, this is a short disclaimer that I am co-founder and advisor for UVO, which is a spin-off company of Scuola superiore Sant'Anna. And basically also part of the contents of this presentation are related to activities that are carried out by UVO. So the summary of the presentation is here. I will briefly introduce the topic of occupational exoskeletons and human-robot synergy. And the idea is to give you an overview of 2 case studies. I will touch on a spring-loaded upper limb exoskeleton that has been developed by UVO. And I'll touch on a powered lumbar exoskeleton developed by Scuola superiore Sant'Anna. And I'll try to draw some conclusions about these 2 different types of technologies. So first of all, we all know that the world population is aging. This is a phenomenon that is affecting our societies, and it's also affecting the workers' population. We know that the aging process can challenge the workers' ability to perform physically demanding tasks without occurring injury. And so the numbers tell us that the majority of occupational diseases basically occur on the musculoskeletal systems of the workers. And this is particularly important when, in age ranges that go from, say, 50 to 64 years old. So basically, occupational diseases increase with aging of the workers' population. So occupational exoskeletons in this context have been developed and proposed as tools that can relieve the workers from excessive physical fatigue, particularly in strenuous tasks and repetitive tasks. And this, I would say, is a kind of short-term objective of the technology. So basically, in the short term, the idea is to reduce the load on specific joints that the exoskeletons aim to assist. Whereas on the long term, the idea is reducing the risks of developing musculoskeletal diseases. And this is something that, of course, needs to be proved, has not been proven yet, let's say. And of course, if this is, turns out to be true, the idea is that we can improve the workers' quality of life by means of this technology. So to date, the present of the exoskeletons for workers sees a number of different commercial devices. There are different devices on the market, and there are really a lot of research prototypes developed by university teams. We can classify them as passive exoskeletons for lower limb support. I'm just mentioning here a few commercial devices you can find on the market, so like the chairless chair, or passive exoskeletons for lumbar support to assist for mostly static trunk flexion tasks. There are passive exoskeletons for the upper limbs for overhead manipulation, and in some cases also repetitive tasks. And you may find combined systems, so systems that combine lumbar and upper limb devices. And there are also powered exoskeletons, particularly we can find them on the market for lumbar support, and here to support for dynamic trunk flexion tasks. So there are 2 main approaches to provide assistance by means of exoskeletons in general. There are passive devices and powered devices. And I think that human-robot synergy is achieved in 2 different ways in passive and active systems. Particularly, we have in passive systems that the torque versus angle relationship is something that is static. We could say that it is embedded into the mechanical structure of the exoskeleton. So by means of a smart mechanical design, you can realize systems that can act synergistically with the users. Whereas with powered exoskeleton, of course, you have more versatility of the control thanks to the control system. So you don't have a fixed static torque versus angle relationship. Also, torque versus phase or torque versus task is something that can be dynamically adapted thanks to the control strategies. So these two different approaches, of course, bring to different challenges in terms of realizing systems that can act in a synergistic way with the users. So today I want to touch on these two case studies that, of course, address or focus on this same challenge by following two different perspectives. So the first one is a spring-loaded upper limb exoskeleton, which is the one you can see in the picture here. So initially, when together with Yuvo and Kumao, we started to develop this system, we wanted to develop a novel passive exoskeleton for shoulder support that could be light, compact, and particularly highly compatible with the human shoulder kinematics. So that was one of the main challenges that we wanted to face. We realized a system that can provide lumbar support as well as upper limb support and gentle assistance. The target end users that we had in mind were workers that perform tasks of overhead manipulation of objects, so typically at relatively high shoulder flexion angle, like higher than 80 degrees, but also for repetitive shoulder flexion extension movements. And so we ended up designing the system that you can see in the picture here, which is currently on the market, commercialized by Kumao. MATE is a spring-loaded exoskeleton for upper limb anti-gravitational support. It's made of three main components. It's a kinematic chain of passive degrees of freedom, a torque generator box that basically includes the mechanisms that generate the assistive action of the exoskeleton, and a physical human-machine interface, which is a lumbar support, so the trunk system and the belt that basically transfer the reaction forces and the weight of the device on the pelvic area, and basically transfer that reaction forces thanks to the tight attachment on the iliac crest region. So the system was designed by considering, as I mentioned before, some key design features, particularly to realize human-robot synergy. We paid a lot of attention on some design features, and in particular, we say that one of the key features of this system is the physiological torque profile. So basically, we looked into what happens into the gravitational torque profile at the glenohumeral joint of the shoulder, and we replicated the same kind of function into the mechanism that basically provides the assistance on the exoskeleton. So this one is a physiological gravitational torque that is experienced by the glenohumeral joint. And basically, this has a null torque when the arm lays down along the human body and reaches the peak value around at 90 degrees of shoulder flexion. So we embedded the same kind of behavior into the assistive torque profile that our system can deliver. So basically, the system does not deliver any torque when the person is laying with his arms along the body, whereas this torque basically increases together with the shoulder flexion angle and provides a part of the gravity torque that the user should exert otherwise. So we say that this is a partial anti-gravitational support. The second key design feature that we think realizes what we call human-robot synergy is related to the kinematic chain. So we embedded into the system a number of passive degrees of freedom that are described by these red arrows here. So we have translational and rotational passive degrees of freedom that basically can comply with the physiological translational movement of the glenohumeral joint during movement. So we have retraction, protraction, we have elevation of the glenohumeral joint, and we want to comply with that. So in order to apply assistance, always in the right plane and in the right direction. So in addition to these two key design features, we also wanted to embed some safety and usability features. So we made the exoskeleton with low and almost constant encumbrance outside the operator's body to avoid hindering the interactions with the environment. We limited the protruding parts so that also the interaction with the environment would be more comfortable. We closed all the mechanisms inside closed enclosures with rounded external shapes, and we tried to leave the area around the head quite free, so to avoid hitting protective equipment that the workers can wear in daily life. We also developed 2 sizes and a number of regulations to fit the device on users with different anthropometries for comfort reasons. So the development phase went through a number of activities in terms of assessment of the effectiveness of this technology. First of all, we run, and we are currently also running experiments in laboratory conditions, but of course what we were also interested in is on-field short-term and long-term tests. So this is a stepwise process approach, that we followed for the assessment of the technology. Going to laboratory tests, the main idea of the test we carried out was to assess the effect of the exoskeleton on shoulder muscles, the kinematics, and the stability of the human-machine interface to understand whether this human-robot synergy that we have, that I have described before, was actually successful. So to do so, we measured the EMG activities on the shoulder muscles, we measured the kinematics of the upper limbs, and we measured the relative displacement of the exoskeleton with respect to the trunk. We did that thanks to motion tracking system and superficial EMG systems. So we measured shoulder and elbow range of motion in free and exo conditions and physical human-machine displacement, thanks to the markers that you can see here. And so the relative displacement between these 2 markers allow us to understand if there is a relative movement. So there are parasitic forces that the exoskeleton is kind of taking if the kinematic compliance is not realized. And superficial EMG was measured on the main superficial muscles of the upper limb, as well as on the latissimus dorsi, which is an extensor muscle on the trunk, to see the effect also on that body part. We measured EMGs, and we extracted features related to the normalized integral of the EMG muscle, segmented into different cycles in repetitive movements. So we've tested different tasks. Here you can see the task that we carried out overhead. Sorry about that. So overhead tasks. We run antero-posterior tasks, which you should be able to see here, maybe. And then internal medial lateral, external medial lateral, and circumferences. So 4 different types of overhead tasks, and we measure these 8 EMG signals. What you see here is the absolute value of the EMG parameters and the relative difference between the 2 conditions of all these different muscles as explained here. So what we can see is that in all overhead tasks, for all the muscles that we measured, both agonist and antagonist muscles, we basically came to a reduction of the muscle activity. So this, of course, is interesting, and it's in line with the hypothesis for agonist muscles, but it's also interesting to see that also posterior deltoid and triceps basically went through reductions of their activity. Range of motion did not change that much between the 2 different conditions, except for some specific cases. And the physical human-machine interface displacement was like less than 1 millimeter, which means that the user does not even realize that there is a relative movement between the 2 systems. Similar results were achieved in repetitive tasks. So here we run a frontal, internal, and external repetitive reaching movements. And we found, again, a significant reduction of the agonist muscles. In this case, the posterior deltoid was increasing in the 3 different tasks according to the idea that, of course, to maintain a certain pace during the movement, the user may be requested to basically exert an extension force, which is higher in the case of the exoskeleton. Again, we did not report any relevant variation of the range of motion, and the physical human-machine interface displacement was really low also in this case. We took 5 millimeter of displacement as our reference, which is what can be perceived by the user and could cause discomfort. Same applies to the static and quasi-static tasks that we tested. Here we asked the subject to maintain some postures and to perform some sinusoidal movements on a screen. And here we also saw a reduction, a significant reduction of all, almost all EMG muscles with no changes of the range of motion and very low displacement of the human-machine interface. So that basically concluded our activities in terms of laboratory studies. What we are doing now, and we are very much interested in, is what happens with these efficacy-related metrics when we go on the field. What we are doing is testing with a kind of slightly different protocol, but similar metrics. Also in field studies, up to date, we have more than 100 operators that participated to our test activities. We run tests in enclosure production lines, service providers, or photovoltaic panel assembly, or appliance assembly, or waste collection. Here we're gaining knowledge on the efficacy of the exoskeletons across different domains, but also on the possible barriers to adoption that there may be when you bring an exoskeleton to the actual field. Fortunately, I do not have results to show because we have a couple of publications under review, so we are now waiting for those publications to be public. But of course, this was just to give you an idea of the roadmap that we have in mind for the assessment. So the second use case that I want to talk about is related to a powered lumbar exoskeleton that we are developing and we're working on at Scuola Superiore Sant'Anna. And basically, it's a powered device that could be used for providing net positive power in lifting operations. Here, any power device, any power exoskeleton, of course, should rely on adaptive controllers, which means that adaptive controllers should be able to recognize different phases of the movement that the user does, and should be able to deal with the movement task and environment variability. So a number of adaptive controllers have been proposed for rhythmic movements like walking, based on tools that can provide a phase in real time, so that the controller can provide a torque versus phase profile, whereas this has not happened for discrete movements, where majority of the cases the controller rely on proportional EMG or model-based approaches. Model-based approaches, they typically rely on the a priori knowledge of the key movement parameters like the duration, the onset timing, and the initial final position of the intended movement. So the objective of our research was to develop an adaptive control for discrete tasks that does not require an a priori knowledge of the key movement parameters. And so to do so, we used active pelvis orthosis that you can see in the picture here. It's a bilateral hip exoskeleton that can provide flexion extension assistance. It's based on series elastic actuation. It weighs 8 kilograms. And basically, it can provide an extension torque at the leg that basically can result in a reaction torque at the trunk. And so it can basically apply an extension torque at the legs and at the trunk that can basically allow the user, facilitate the user in lifting operations. So the idea here is that the control architecture, which is shown in the picture here, should recognize when the user is flexing the trunk and recognize the onset of the extension movement of the trunk, so to provide a different assistance in flexion and in extension phases. Of course, in both flexion and extension phases, the system wants to provide extension torque in order to simulate the action of the extensor muscles of the trunk. But according to the biological torque profile in the extension phase, we want to provide a higher level of torque. So to do this, what we developed is an intention decoding algorithm that basically detects the initial extension phase of the lifting movement. And we developed a phase estimation of the discrete task. So basically, according to these two modules, we have an assistive torque that basically can compute a desired torque profile that can go to the low-level control of the system. So here are a little bit more details, but I don't have time to go through the mathematics of these, but you can find all the details in this very recent paper we published on transactional robotics. Basically, the main idea here is that we have, for the first time, an adaptive dynamic movement primitive controller that is capable of basically computing the phase of a discrete movement in real time and predict the evolution of the movement with a certain phase lead, which we set at 10% of the whole movement. So based on the prediction of the movement, we are able to develop an assistive torque that can change through these two different phases. So flexion phase, we provide a spring-like behavior with a fixed equilibrium position. So basically, the theta basically equal to 0. Whereas in the extension phase, we developed a spring-like control with equilibrium position on the predicted movement. So we developed this impedance control mode that allows us to have an assistive profile that in the extension phase provides a much higher torque with a peak torque that basically is almost synchronous with the middle of the movement in the extension. So we tested these control strategies, in different tasks. So as I said, the system does not require any a priori knowledge of the movement. So the initial, final position, the speed of the movement, it just in real time adapts its internal parameters. And so we tested what happened with 10 different types of lifting tasks at different speeds, at different positions, and different symmetrical conditions in zero torque and assistive modes. And we basically computed a number of metrics to understand whether the system was able to compute the phase in real time and predict the movement accurately. So we computed the phase of the movement, the phase lead movement prediction, and the end angle of the movement. And we basically found that the system is quite good in estimating the phase with a phase linearity, which is pretty good in both conditions. The phase lead prediction is also quite good, so we are quite capable of predicting the evolution of the movement in different conditions. So these are the 10 lifting tasks that we tested, and also the end angle error was really kind of low, so we were quite satisfied with the performance of the controller. So after that, we tested the controller also with human subject testing. We wanted to see the effectiveness of this assistive strategy in symmetrical lifting tasks. In this case, we compared the assistive mode with the zero torque control and with no exo. So in these 3 different conditions, we measured the full body kinematics and EMG on the lower limb and trunk extensor muscles. And basically, what we found was that in terms of kinematics, the time to extend the trunk basically decreases when the assistance is on. So it takes shorter time to complete the task when the assistance is there. And in terms of kinematics, which you can see here, and the range of motions you can see here in the 3 different conditions, we found that in the exo AM condition, there is a decreased trunk forward bending. So this is something you can see here. So it's kind of reduced range of motion in the flexion phase, whereas we did not find any changes in the kinematics of the knee and ankle joints. And interesting results on EMG are that in the extension phase, we found significant decrease of the low back muscles in the exo-EAM condition. We also found a reduced muscle activity in the transparent mode compared to the no exo condition, which is interesting, and we could explain that thanks to the loading effect of wearing the APO. So basically, thanks to the mass that we add on the back of the user, we can exploit that mass to basically provide a kind of inherent extension torque just by wearing the device. And in the flexion phase, we saw a significant reduction in the low back muscles activity in assistive mode while flexing, related to the reduced forward bending of the users. Of course, this can be related both to the assistance, but also to the reduced forward bending of the users. So just to draw conclusions, I think that passive and active exoskeletons could face different issues in terms of human-robot synergy. They face this topic from different perspectives. Passive devices are grounded on embodied intelligence, whereas active devices need more sophisticated software solutions, control solutions. In one case, passive devices are ready for large-scale adoption, and in this case, longitudinal studies are necessary to prove the long-term effectiveness of these devices, whereas powered exoskeletons are, of course, a promising technology, but their systematic adoption requires some effort. So this concludes the presentation. I just want to take the opportunity to just say a few words on a new journal that has been launched by Cambridge University Press, which is Wearable Technologies. I would invite all the attendees to look what the journal is, the objectives. So the journal deals, of course, with wearable exoskeletons and sensors, any wearable technology. So if you have any interest or papers, this journal would be interested in publishing. Yeah, so that concludes the talk.
Thank you very much, Simona, for this very, very nice and very interesting talk. So now we will take a few questions. So for now, we have one question from the audience, which is why there is only spring-like control and why not using dumping-like control part as well? So I guess it's for the active exo.
Yeah, okay. I don't know if you're still able to see my screen. I can stop sharing, by the way.
Yeah.
Okay. Yeah, okay. So in that case, we basically tried to simulate or to compute torque versus space profile that would kind of match the biological torque profile that the extensor muscles exert during flexion and extension movements. So we found, of course, this first idea of a spring-like approach, but of course, even more complex. The systems could be, effective for the same purpose.
Thank you. So do we have, okay, I'm just checking if we have other questions. Otherwise, so I do have very small questions, but I was wondering, especially for the active system, did you have to use it with like both legs doing approximately the same motions, or could you, would it still be working if you were doing like, 1 foot behind and 1 foot really, 1 foot like front and 1 foot really behind with a very asymmetrical motion?
Yeah, thank you for the question. Yeah, so basically, the same control framework is applied to the two different joints and works independently for the two different joints. So as soon as we have a phase estimation that runs for the left and right sides, we can compute different torques for the two sizes. So we don't have the movement necessarily to be symmetrical. So the control framework is very versatile, and the idea was really to avoid taking any a priori knowledge of the movement. So the system works in parallel and independently for the two sizes, and the two sizes, they can start with the with their initial position and final position could be different, and the duration of the task can be different in the two sizes. That was the idea. So it makes the system intrinsically capable of dealing with very asymmetrical movements. Yeah.
Thank you very much, and I will definitely check the paper.
Thank you.
If we have one more question, we can take it. And okay, there is no. I think the comment is rather from Daniele has a question, but I think it's a comment. So thank you very much again, Simona.